Well, good morning, everyone. My name is Lauren Dow. I'm the Communications Coordinator for the National Road Research Alliance, and I want to welcome you to today's presentation of Research Pays Off. And to start with, I'm going to hand it over to Ben to give us a few updates from the NRRA.
Yeah, thank you, Lauren, and everyone, welcome to the Research Pays Off. I wanted to go over a couple things that I thought was pretty exciting, and you may have heard from me already, but I went through and summarized kind of what's going on currently with NRRA, and it's pretty exciting to have 8 states and Illinois Tollway working together. We have over 55 different associate members, which is great. I guess the whole goal we're trying to do is communicate our expertise and share results. That goes a long way. We're a pooled fund now that we have probably over $4.4 million that we've put towards this. And that's great because we've been able to fund 37 different projects, wide range of, I almost went into my wide range of pavement research where, we've been doing a lot with the money that we have, and with 37 projects. If you check out our website, there's a lot going on there, and appreciate everyone's efforts to do that. Some of the current projects right now for the call for innovation that we're working on the contracting right now. Some are a little different contracts because they have to do with partnerships. But again, those the goals, and I think I really appreciate everyone's efforts on getting those work plans approved so we can get those contracts developed, and all the hard work that's been going on with the research teams. And again, MnDOT has seen a lot of benefit already. When you look at our investment, it is $150,000 a year. We've done 5 years, say, but that's 6 times the amount of research we could have done normally. So again, that's really a great benefit right there, and it's really helped us retain our quality staff that we have here, and we really appreciate that. And I think MnRoad has gained a lot too because of the regional and national exposure we've gotten so far. A couple things that are coming up in the near future. Again, TRB is coming up, starts January 12th. We'll have a TRB booth there for NRRA. We welcome people to come down and see us. Great to have you there. Bring some of your friends, coworkers, others that you know that may not know as much about NRRA. We'd like to introduce them to it. Again, other members that you might know of for other states and friends that you have around the country, it'd be great to see them at the booth. And again, there's sign-ups. Lauren has that in the newsletter. There's a link you can go to and put your name down for different times. Even if that whole slot looks like it's pretty busy at that time and you have some free time, please come down and join us anyways. I'll try to be there as much as I can. I don't have any of my times on there, but again, we'll all be welcoming you there. We also have an open house session Wednesday from 6:30 to 8 o'clock. That's January 15th. It's at Marriott Chinatown M3 room. And again, here's the goals: to introduce others to NRRA, bring other states, get together, talk face-to-face. We've done so much stuff online. We've saved a lot of money by doing that, but there's nothing better than seeing people and kind of seeing them firsthand. So please come and join us that Wednesday. That would be great. Other than that, again, thanks for all your support and efforts, and I'll let Lauren introduce Tom.
Thanks, Ben. Today we have Tom Burnham, who is a senior road research engineer here at MnDOT in our Office of Materials and Road Research, and he's a part of the rigid team of the NRRA, part of the friends and supporting staff for that team, and is pretty active and involved with all things concrete. So we're excited to hear from him today, and I will pass it over to him.
Okay, thanks, Lauren. I think we maybe should tell people to type in your questions, and then we'll address them at the end so we can put people on mute so we don't have interruptions during the presentation. So thank you again today for this opportunity to talk about a non-destructive technique that it's been around a while, but it's gaining a lot of popularity, especially for diagnosing issues with concrete pavements, and that's where our focus has been. We've gotten into this business purchasing a device last winter, and we spent the summer out kind of playing with it on the ground, and we're gaining a lot of confidence, and kind of want to share some of those experiences that we've had as we've gotten used to this device. Before I begin, I'd like to acknowledge the help I've had this year. Mike Walls has been a student worker working in our department. He's really been instrumental in a lot of the analysis and actually being out in the field, helping me take the measurements. Gordy Broom with our MnDOT concrete office has led us to a lot of opportunities to use the device. So we thank him, and of course we always thank the traffic control people that keep us alive when we're out testing on these roads. So a little background, what is ultrasonic tomography? It's really ultrasonic or ultrasound, the sound waves that are frequencies higher than are audible. So it's pretty simple as that. And tomography is a technique for displaying the insides of things, cross-section through, again, it's used by doctors for human body or solid objects. That's kind of what we're using it for, is for concrete. And really what it involves is projections of velocity or attenuation of measurements of ultrasonic pulses. Sounds complicated, but it's a wonderful tool. So why do we think we want to use it for concrete? Well, a lot of things. This technology is very good at actually helping us detect slab thickness. Again, non-destructive. We don't need a core. We can put this device down and get a fairly accurate slab thickness. And then, of course, the other feature, of course, is the detection or mapping of various things, whether it's locating reinforcement, searching for delamination, getting an idea where cracks are headed or if they exist, and then, of course, voids. As I mentioned at the beginning, this technique has been around a while. However, it's been kind of accelerating lately. We actually had a study back in 2016 with Lev Kazanovich and Kyle Hood, who is now on our staff, heavily involved in taking this technique around and giving us an idea of the pavement thickness variability in our system. So that played an instrumental role in understanding kind of the variability that's going on in concrete pavement thickness. The University of Illinois in Urbana-Champaign has also been actively using this technique, and they produced a couple of reports in 2017 and again this year. Again, looking at assessing the condition of the pavement, quality assurance, and something else is joint activation. That's another thing that I'll be talking a lot about. In a similar fashion, this spring, the Iowa State University CP Tech Center also produced a report, and a large portion of that was, again, using this technique to determine joint activation. So the particular device we use for this ultrasonic tomography, in our case, is an ACS A1040 MIRA device. We simply refer to it as the MIRA device. And it's a handheld device. It's about 14 inches long by 4 inches wide. And you can see by the depictions here, it involves sending ultrasonic signals back down to bounce off of various surfaces. So when it hits a solid surface or something that interrupts the sound signal and receives back, it'll kind of portray an image. And what's nice, again, is it really has a lot of signals. It's not just like our old technique with impulse echo where you're pounding it once and then you're listening. Because of the array of sensors, we can get a much higher definition of what we see within the concrete pavement. So in this case, you have 48 transducers. Again, the ultrasonic operating frequency is 25 to 85 kilohertz. And the manufacturer claims that in plain concrete, you can detect down to 6.5 feet of depth using this device. We have not tested that claim, and you'll notice for reinforced concrete, that's much less, probably again with signals being attenuated by the steel. The device is capable of both kind of live snapshots as well as recorded data. And from that data, we're able to make both 2-dimensional and 3-dimensional renderings, which is very interesting. So a couple limitations. There's always limitations. The devices are not the ultimate magic box that we'd like them to be. Obviously, this is not an X-ray device, so your definitions and what you see are not going to look like an X-ray. We would love to have an X-ray, and I understand there are efforts towards that, but even at this point, it requires injecting some kind of a tracer element into the concrete, which of course gets a little bit challenging out in the field. Because of the flat nature of the surface, it will not work very well on curved surfaces. And also, it's not really intended for a very, very small surface area. You can use it, but you're not going to get the definition because you're involving far fewer sensors. Near joint slabs and edges, there are shadowed regions because of the nature of where the sound signals are bouncing off of. So that presents a little bit of challenge, again, definition near joints and slab edges. It is a point measurement device. In other words, it takes quite an effort to map an area, but it's a very convenient tool if you want to just kind of poke around and do individual measurements. And again, images near reinforcement are not, it's not an X-ray. You get an indication that the reinforcement's there, but it's not a clear-cut dimensional thing that you can measure. So this portrays what you see in the two-dimensional mode or the live mode. And what's nice is you set this device down and you press the button on the handle, and within 5 seconds you get an image like this. So it's a very quick device. And from it, you're going to get something that looks like this image here. It also has the capability of moving these cursors around, and then it'll tell you exactly where it is. So in case you want to kind of estimate where a particular feature is, it'll give you some pretty well to scale measurements. It also portrays the frequency band response. So there's a bunch of information on this particular screen. In this mode, it's intended for walking around and taking a snapshot and kind of seeing what's going on. The data is not recorded in this mode. In the next mode is the recording mode, and this you can either do two-dimensional or three-dimensional by laying out a grid and then positioning the device at the grid intersection points. So you kind of create a size of your grid, and then you will take a measurement, and then there's the software, if you're going laterally, will automatically advance, and then you have to manually bring it back and start another row. But what this allows you to do is to create a three-dimensional rendering. So again, you can do two-dimensional just by having a row of measurements across, or you can create this grid that will give you a three-dimensional image. So provided with the device is a post-processing software called IntraView Concrete, and again, it's capable of two- and three-dimensional, what I'd say it's colored renderings. And what's very nice is there's very little post-processing. Essentially, you transfer the files from the device to this software, and within a minute, you can pop up actually a three-dimensional image. So it's really great for that. So here's what a typical 2D rendering would look like. And in this case, we've kind of stitched a number of them together. So this is longer than a device, set it down. And this is kind of what you typically see. I'll get a little bit more into details of what you're actually seeing in a couple slides, but kind of this is what you'd see in a two-dimensional. It's essentially a vertical slice right below where you set down the device. So it's a profile view. And then this would be a three-dimensional rendering. So again, if you take it out and do measurements along at these grid intersections, you can get this view, which, again, using the software, you can rotate it around, and it really allows you to see various things. This happens to be kind of a colored thing. There's also a grayscale with yellowing, and so there's a number of features you can kind of play around with to see if you can better define or get a better indication of what is going on within the concrete itself. So now I'm just going to kind of step through some of the things we've been measuring and getting comfortable with. Again, the first one is slab thickness. We don't want to be poking cores if we don't have to, and we often don't have this opportunity here where you have to shoulder off and you can physically measure the thickness of a concrete. You'd like to just be able to take a tool out and measure it. So that's what we did here, and you can see this response, which again we saw a couple slides ago. And this is a stitched together image, so it's a couple feet long. But what it indicates by this strong return here is that this is the bottom of the slab. And you can see by going across and stitching them together, there's actually a little bit of variation on the bottom, which is typically what we might see. And the understanding is that you have this colored blob, and if you take and put a line through the middle of it, that's a fairly accurate indication of how deep your concrete is. It's pretty good. Often you get, often you get this second reflection at the bottom again, and we understand that it's just a reflection of the sound waves bouncing again off probably the surface in this case, but you're mostly interested in the strong colored returns that you get, your first return that you get on your image. As part of another experiment, we had some experimental slabs that Monroe created with intentional voids in them. So we wanted to kind of see what we could see with this device, of course, because we'd understand what actually it should detect. In this case, we have a nice TP-shaped bottom gone. And this is kind of the image that we got by putting it across the joint. So again, you're going to see some features here. You do kind of see one wall of that feature right here. You don't see it on the other side. You also see, again, what I'm saying is when there's a pretty clear and defined crack or joint, you get some shadowing right near, so the sound signals can't go across, so they can't portray anything. So again, this is, as I claimed before, it's not an X-ray machine. You don't see the exact shape, but it'll give you some indication that something is angled or curved down below. Here's another one where there was an intentional void created. This is the image that we get. Again, you don't see an actual circle. There are some features in the software that actually will kind of generate that circle, but in this particular case with these colors, you can indicate, again, there's some kind of a large gap. If it was a solid surface, you'd see a nice solid red line across the bottom. So again, you put this down, you could say, yes, there's something going on within that joint, and it's larger than just a crack, because it's such a wide gap between these signals. So thanks to the Concrete Office, we had some opportunities to go out onto some rehabilitation jobs and see if we could help with the assessment of what's going on. And really want to emphasize that this particular tool, because it's a point tool, it's difficult to cover large areas, so it's still very good to use the old-fashioned chain, because you can really rapidly detect areas that sound different. You can then take this device and focus in on what's really happening below, because the chain will tell you something's wrong, but it won't tell you where in the pavement it's wrong. And in this case, you can see we actually did gather some data, and we also took some cores, and you can see in this case the chain indicated some kind of hollowness. When we took a core at 1, there was a clear delamination going on. At 2, it was back to solid concrete. This is what we get from the mirror image here. So this is the joint, and then we're working our way back away from it. This would have been where we took the core, and sure enough, it clearly indicated a very strong signal right at the exact depth that we saw in our core sample. You go back a ways, core 2, all you're detecting is the bottom, a solid core. In between, again, there's this transition area that it could be a little bit difficult to tell what's going on, but again, this tool is very good at identifying horizontal delamination, because again, the sound signals will bounce right off of it. So you won't even see anything at the bottom. It's just overwhelmed by the delamination above. This is another rehabilitation project went out, and we were trying to help the the consultants, it's got a little bit of crazy with their mapping, and we just happened to see, okay, this particular panel was marked as being removed. did he miss something? And we went over and tested this side just to see what's going on. And this is kind of the result we got. Was there's a lot of variable depth going on. It's potential joint deterioration. We did pull a core sample, which unfortunately we did not take a photograph of or keep, but it did show a very uneven bottom. So in this case, it could be that they'll remove this and fix this, but maybe this particular sap should have been removed because there's a lot of deterioration potential on that side. Moving on to the detection of joint deployment. It's something we're very interested in now that we're constructing a lot of overlays, and we're trying to get all these small panels to deploy so that they function better. This happens to be a fiber reinforced project that we were out on. We didn't have an opportunity yet to really map this extensively. But this happened to be one where they actually intentionally loaded it early to try to encourage joint deployment. This is kind of the typical views that we get to determine whether we feel it's deployed or not. If it's deployed, and we just drew a saw cut on here, this is not what you'd see in the signal, you're going to see some kind of an interruption below it's not a solid surface below. As opposed to here, you have a saw cut and there's a nice solid surface, meaning there's very little chance that that joint has deployed and cracked through. So it's pretty fairly, very easy to see whether it's deployed or not. I know some of the studies have gotten into very sophisticated analysis of looking at various sensor combinations on the device, but I think we feel comfortable enough if you're going to make an assessment, you can pretty much clearly tell the difference between this and this without having to do high-end calculations. Here's another example here is this particular ramp apparently got sawed a little bit late, so they had some sympathetic cracking. They were interested in, wondering, even though you don't see that down here at the bottom, did this also deploy as well? So we took our scan, and again, it's not an X-ray machine, but we can kind of tell by the strength of the signal on the one side below the saw cut that it did not crack, and that's what we saw at the end of the pavement. This is a side view, this happens to be a top view. And because of this shadowing or inability as you get near a crack that you don't get a response, we still feel fairly confident that because of this strong signal so close to this sawed crack, that it is not deployed. So as you can see, there's a little bit of subjective judgment in viewing these signals, but nevertheless, it does give you the opportunity to kind of see things are not solid or where we believe the cracking is headed. This particular example was a project where they had some early cracking and they were asking the contractor to go out and do a little bit of route and seal, which is kind of unusual for a concrete. But nevertheless, they were kind of doing a shallow route and then filling and sealing. I had the question is, they were kind of doing it visually from the surface. The question was, did this continue? Because we don't see anything on the surface. Again, this is a top view. This happened to be here, the visible crack. And then from here, you can kind of see it's probably a strong possibility that there's a hidden crack that is about to form as we go. So again, this tool can kind of give you some indications to further assess the situation. This particular project was kind of a demonstration in helping out the Wisconsin DOT over in Menominee, Wisconsin. You can see there's some depressions at a number of dull bars. They felt there was some pore consolidation going on, so we brought this tool out to kind of assess what we could see. And this is what we saw. We were able to see the tie bar. We also saw some lighter colored indications, but we would interpret as potential voids, similar down here near the tie bar. And I say potential because, again, the resolution on these things is not exact, but it is definitely not a darker color, so you understand that there could be something going on. You also see here that this was not at a joint, but you can see that there was enough color going across that you felt that it was not cracked through. However, again, because of the dominance of this tie bar and the signals coming down, it did show a little bit of a break down here. At another location, again, we saw the tie bar, but next to it was a kind of a strong feature. This you'd have less doubt that there was some kind of a void or debris that got built into the system. Again, down here at the bottom, you're seeing a little bit of shadowing, the effect of the sound being bounced off that and not making it to the bottom. And finally, this one where, again, very strong, clean signal on the tie bar. Unfortunately, it's probably not at the depth, and we found a number that were pretty shallow, and there was some concern there. So, in this case, perhaps because the bar is so high, we had that nice solid bottom indicating there's no cracking below it. So in summary, the mirror device is, we're finding to be a very handy tool for quick, non-destructive evaluation of concrete. And hopefully, as I've shown, it's not an exact X-ray machine, but it is very good at identifying as-built slab depths, delamination, propagation of cracks, joint deployment, location of reinforcement, and other anomalies in the concrete matrix. I've also hopefully shown that there has limitations. When you get near edges and joints, you don't get a lot of detail, and that's a little bit unfortunate, but that's kind of the nature of the technique. So what's next for us here at MnDOT is we're going to continue testing different applications. We'll continue, of course, strong focus on pavements, whether it's rehab, construction issues. Perhaps get it involved in determining, early opening of projects. I think there's something we took it out a little bit this summer and had an opportunity and a job to determine how soon you could use this device. And the pavement has to be quite stiff before you get accurate readings. So that, it may not be a good tool for that, but that's something we're going to continue to research. Some other opportunities, of course, it seems like it'd be an ideal job for detecting delamination in bridge decks. We haven't been approached by our MnDOT bridge office yet, but I'm waiting for their call any day. Other concrete structures, we actually have a unique opportunity to go out and check out a municipal pool deck for the location of reinforcement, I understand. And I also see perhaps they could get involved in some assessment of footings. Again, we can see that, you can get signals down to 6.5 feet deep. So perhaps there's some opportunities for assessing issues that might be showing up with footings. We will, of course, our prominent use again probably be joint deployment, whether it's naturally occurring overlays or our efforts into intentionally early loading to get them to deploy. And this would be a very good tool to determine how effective we are at that, rather than kind of looking at the edge of the pavement. We are going to create a simpler user guide. The one that comes with the device is not real straightforward. It took us quite a bit to get up to speed, but we feel we can really simplify the user guide. And then from there, of course, we want to hand this off and implement this device in the department by training interested users. And a lot of times producing a video is a very effective way to do that, so we have plans for that. And I'll close out with this new invention that Mike Walsh, the student worker, came up with. We got tired of drawing chalk on the pavement, so we came up with this nice lightweight thing with it's simply strings strung across it. We can set down the vise and use it to map out our three-dimensional grid. So with that, I'll take any questions that have come up. I don't know, Lauren, do you want to, let's see.
Just read it. Read.
Oh, read, okay, there we go. We have one question here.
Tom, I guess this has been Worrell. I have a question for you. So if you had a 5-mile job of full depth repairs, joint repairs, how do you best utilize this for helping that out with that, or is that what? I mean, you chain drag it and do all that stuff, and it's a huge issue of trying to find out the quantities. And it's so hard to get them off. It's so easy to get them off, I should say. What could this do for you?
I think there's a lot of, again, the chain is going to kind of give you an overall feel, but there's always questions of whether it should be a full depth or partial depth repair. So this is going to be the tool you want. It'd be nice to have more of them, of course, so that you can have multiple people out kind of mapping out an area. They're quite expensive at this point. We're hoping.
What was the cost of this?
This one in particular costs $36,000, so it's a pretty spendy tool right now.
Are there other comparable devices out there?
I did a little search this morning and I only saw one other device that's a handheld device that's somewhat similar to this. It doesn't quite have as many sensors on it. So this device is fairly unique still. And I guess, as with most of this technology, the more you sell, eventually the cost will come down. But they definitely need more users at this point. Yes.
Very, very interesting that we're at the stage where we now have this device. It used to sound like a mystery when the only time we heard about it was when somebody was using it at the University of Minnesota. Then it was really a mystery to us. But now we have this device and we're already using it in projects in the network. That's very interesting. The one thing though, the area of my interest is the string that opening to traffic. In most cases, the kind of things we are detecting are highly quantitative. We're not looking at probably the color code, or we are using pulse velocity, and you didn't mention pulse velocity throughout your presentation. So could you shed light on that area? Because we did have a map of places where on the wheel track, and just between wheel tracks, so that we can see this area spread and the actual dichotomy between the areas that were loaded directly by the wheels and the areas between wheel bars. And the only thing we could use was pulse velocity. So what's your take on that? I mean, how do we, right now, what I hear that there's only one person in this country who has a code for extracting the pulse velocity. Such things are not good. So do you have any discussion with the manufacturers or somebody on how we can crack that code and be able to at least read pulse velocity in our measurement?
Yeah, we haven't quite gone down that avenue yet. And I agree that some effort needs to be put in for what you're talking about. Right now, we're trying to keep it a simple tool for the user. But I think, again, as we develop this tool more, we will address getting into that. I'm not, I would assume that that information is stored in a file. It's just a matter of having the way to open up the file and utilize that information. Live information, I do believe you get a result on the screen showing the frequency, but again, you'd like to record that. So yes, I think that's
I have three questions here.
Sure.
The first one is, do you need to have the surface prepared somehow? Is that these sensors are dry contact sensors? Do you have to have it dry or can be wet? Do you have to have any special preparation for the readings to get properly taken?
I think you'd want dry. They're all spring loaded when you set it down, so they're all spring loaded, so they should take care of any kind of irregularities in the surface. I'm not sure about that, about whether it needs to be completely dry.
Or there's debris, debris.
Yeah, no debris, of course, yeah. Anything that would have an effect on the sound signal.
Reflecting.
Yeah.
The second one is the contour plot you were showing, that's shear wave velocity, or what is that? What units, what measurement are you showing? Those colors are reflectance or like wavelength, like what wavelength?
It's velocity.
Velocity?
Yeah, velocities.
Okay.
Yeah.
And then for the future, you mentioned you're going to be measuring pavements. That includes asphalt. Are you considering using it in asphalt too?
Now, that question gets asked frequently, and there has been attempts, I believe Kyle said that he has attempted, but that was not as successful as they would like to be. It's just Kyle Hoyg. Yeah. He said the velocities are much different within the asphalt. It's not as stiff and as rich, the speed of the signal, so it was not as successful getting something out of using an asphalt compared to a concrete, which is a very rapid speed of the return of the sound waves.
Okay, thanks.
I have one comment. Maybe this could help with what we're doing too. With the road doctor, we've been surveying on I-94, because the I-94 has been changed the entire, and they have mapped all the repair. They have found out all the areas, they have mapped all the areas where they have the damnation, and we need this concrete. What we're trying to do is if we can replicate with the thermal camera that we have in the road doctor to see by thermal contrast between the surface and the voids to locate those areas and to see if we can basically capture the areas that have been changed. Maybe that could help you then once we have done the entire mile, because we measured 1 or 2 miles, probably you can go look in there and see, look deeper on those areas.
Yes.
One thing that we found we tested only one night, I-94, we found that the areas beneath the bridge were much warmer than, so that we're still finding to filter out the areas, but I think we will be able to provide you those areas where the suspect areas or locations that needs to be further looked into.
Yeah.
Probably that could be something that I will show you the data.
Sure.
Tom, I have one more question. This is Ben Worrell with MnDOT. This is kind of a point and shoot or drop and shoot type equipment. Would there be any thought, or has there been any thought about having some sort of gator or something to make this kind of run down the road? Is there anyone thinking of these Dr. Seuss equipment for this type of stuff? We're having good luck with the DPS.
Put in the Kyle's role.
Yeah. But, that would be the ultimate, I would say, time like the road doctor with MnDOT has, with the cameras, with temperatures and things like that.
I believe there has been companies in the past, I think it's Olson Engineering or something, trying to develop some kind of a rolling impact echo kind of device that would bend that philosophy.
Okay.
I'm not sure it was successful. And I know Bernard has had lots of thoughts storming in his head over the years. I don't think he's ever had a chance to really fully develop them with. Yeah, same thing. This is a great point and shoot device. We need mapping for efficiency and safety and that type of thing.
What frequency are you using at? What are the range of frequencies? 25?
No, that's the sonic symbol. Getting what the numbers, if it's 3,500. We've adjusted it because as we've used it, there's a default. I think 3,700 is the default. We've lowered that because we find we can get better definition, especially if we're trying to detect whether the joints are deployed or not. Okay. So we've been kind of playing around, and that was also noted by our state too. Then we really did a whole range, and we did a little bit of analysis too, just trying to alter this frequency to see how we could better get a response for the particular application we're using.
Just to say a little bit about what you said, the impact echo is still being used. We used it Highway 7 some years ago when there was some poorly mixed concrete. Boston Engineering used it. It helped to a very large extent. That was in Montevideo some years ago, right? Remember that? Yep. Okay. The device that he was referring to that I'm thinking about is just what he mentioned about the mirror. The mirror, you need to do more work if you want to do something around the joints, because the mirror isn't going to. I don't know. You need more work when you have a joint. For instance, if you have a joint that has a cavity that's invisible from the surface, you have to use extra work to get the mirror to evaluate that. But we have what we call the impedance tube. And that impedance tube sends actually a sound signal through the cavity. And if that cavity expands or enlarges, there's a change in the natural frequency. And as it sends the reflected signal back, that reflected signal is indicating what's happening within that cavity. So if there is an enlargement like the scarring which he showed at the mid-depth, or the beveling at the bottom, we'll be able to use that to identify that there may be beveling, and that there's beveling that has gone all right in the. So that device is still being developed. The original usage of it was for sound absorption, but we just found that it's a very good device for joint deterioration, and that's where both the mirror and the GPR. That's where they have challenges. That joint, the joint itself, if the joint is having a deterioration, you can't see it from the surface, but it's right there at the bottom.
Are there any groups from people logged in outside of MnDOT here? We've had a lot of questions from MnDOT. Do we have any people outside that have questions so far? You can take yourself off mute, or we can unmute so we can have some discussion. Hearing none, we thank you for your participation this morning. Ben, do you have an announcement on the next one?
No, I don't. There is something planned. Lauren, do you have that title?
Let's see. I do have it available on the website. It is listed next month. Oh yes, we'll be hearing from Andrea Blanchett and Shu from WSB on their recently completed projects. And that will be on January 21st.
That sounds good. So I guess the only thing left is everyone have a good holiday season, and we hope to see you all soon at our next meetings.
Oh, we have
and we do have a question. Sure, you would do that, Michael.
A comment.
Again, the RFP is coming out for the Flex Team Rejuvenator projects. It is posted right now. So we got that moving forward, and that was a 2019 effort that was developed. So again, thanks for our help getting that project RFP out, and we hope that any contractors out there will see that RFP. If you have any questions where to get at that, either talk to Michael Vertis or myself. Actually, talk to Michael Vertis because I talked to Michael Vertis about that. That's his project. So thank you. And I guess I'll continue on saying again, have a great holiday season. Hug your family and friends. They're very important. Thanks.